So the plan for today, we're going to go over these questions here. We're going to learn about these things here. I just made a list to make sure I go over. Sometimes I forget to talk about some things because I tend to just go off the top of my head here. But so we're going to talk about review. We're going to review the mass of an electron. I don't know if I told you that. You're supposed to look up those two definitions. We'll talk about that. We're going to review electronegativity and ionization energy. And we'll talk about this thing called nuclear charge, and then how that relates to the tug of war we will be playing. Because really we're learning about radius today, but all of this is related to that. And so radius really, like in the lab, what that means is if you have an atom, you know, from the nucleus to the outer edge, is technically the radius, but that's not the definition. If you looked it up, you should know. All right, so that's the plan for today, and then you have a worksheet due tomorrow. And a quiz next Thursday. What's it going to be on? Everything you've learned about atomic structure. What is that? The gold foil experiment, the models of the atom, protons, neutrons, electrons, ions, radius questions, things like this. Okay? You're going to learn about isotopes, which I brought up yesterday. That will be on that quiz as well. So it's not like a test, but it's more than 10 questions. I don't know how long. I have a quiz. I might make a new one. I don't know. But it's not going to be a whole period, but it's not going to be super short, kind of like in the middle. All right, so that'll be next Thursday. Okay, so now we're good. All the plans are out there. Here we go. How many electrons does a strontium atom have? And you have to tell me how you figured it out. So Adam, you weren't here yesterday. Why don't you give this a shot?
38.
38. How do you know that? Very good.
Because that's the atomic number.
Good. That's the atomic number. So the answer is 38 electrons. True or false? Atoms are neutral. This is for everybody. True. What does neutral mean? No charge. So strontium atom is neutral because it has 38 electrons. How many protons does it have? 38. The atomic number tells you both. If it says this, if it says that, an ion, then the protons, electrons are not balanced. Okay? So this is what we talked about yesterday. How many electrons does a strontium ion have? So the atom looks like this. SR38, oops, not 38. What is it, 88? Yeah, 88 over 38. So SR88 over 38, that's the atom. Who can tell me what would the nuclear symbol be for the ion? Well, the nuclear symbol doesn't change, except we have to add the charge. +2 in the top right corner. So I want to make this clear. I said it yesterday, but I want to repeat it, that when you're writing the nuclear symbol, the only difference between an ion and an atom is you label the ion. How come these two numbers don't change? Talked about it yesterday, but why don't these numbers change if it's an ion? Matt Payne, you with me?
Yeah.
Okay. Courtney.
The mass is in the nucleus.
The mass is in the nucleus.
And what's that +2?
Well, forget the +2. What's this?
Well, those are the
Protons, and that's also in the nucleus. So you have this nucleus where you have protons and neutrons in here, and then the electrons are outside. So whatever's in the nucleus stays the same. These are what change. So this charge is because the number of electrons change, not the protons and neutrons. So those numbers on the chart don't change. Okay, the one on the chart is 88, 38, 38. That's never going to change. So I want to make that clear. So anyways, I think Hannah has the right answer. How many electrons? 36. Right, 36. 36 because neutral strontium has 38 electrons. We just said that, 38. +2 means you lost 2 negative charges, right? You lose something negative, you become more positive. So this should have 38 protons if it's neutral, but because it's +2, it lost 2 electrons, so it has 36 electrons. That's the skill you need to master. Questions on number 2. Okay, 3. Explain which of the following species is more stable. I use this word because students have a hard time with that. They read it, they're like, what do they mean by species? When I say species, what do you think? Animals, humans, whatever, right? In chemistry, the regents will use the word species to mean atom, molecule, ion. I guess that's about it. So that's an atom, that's an ion. They use the word species, that means everything. It means all of the above. So just be familiar with that. So anyways, which one is more stable? F or F minus, you have to explain. Colin.
F minus 1, because with the addition of the new electron, it has a full valence shell.
Perfect answer, very good. That's even a good AP answer. The electron configuration for F is what? Aaliyah, what's that electron configuration for F? That's the atomic number, but I want to know the electron configuration. 2-7, very good. Sorry, I didn't hear you. 2-7, very good. And like Colin said, if it gains 1, right, -1 means it gains a negative. It gains the negative on the outer valence shell, so it becomes 2-8. Yesterday we talked about that the nucleus is right here. Here's your nucleus down here, right? Closer to that first level. So your first shell is really attracted to that nucleus. As you get further away from the nucleus, there's less attraction. So it's easy for electrons to come and go. So when this gains an electron, it gains it here, not on the first level. Okay, first of all, that can't hold anymore. It can only hold 2, but again, it's about that attraction. So he's right, 2-8. This is called a full valence shell or a complete octet. That's why it's more stable. Very good. That's a really good question. All right, so if you understand that, you're in a good spot. If you're a little confused, that's okay. Hopefully, by the end of today and in the future, we'll talk more about that. It'll make more sense. All right, 4. This was a little review. I feel like I haven't stressed this enough. So go to table O. Let's make sure we understand what these things look like. So notation of a proton, neutron, and electron. I sometimes kind of assume, and you know what that means, Matt Payne, right? The problem with assuming?
Sure.
Do you know the phrase I'm talking about?
Not really.
I don't.
No, you guys know what I'm
really.
talking about? I'm not going to say it, I'm getting recorded here, But you get it. I can't always assume,
We can pause the video.
because sometimes, if you assume, it makes a blank out of you and me. Okay, ASS.
There you go.
Okay, what's the notation for proton? Anybody?
Sorry, what's the question?
Proton notation. 1/1h. Good. 1/1h. What's a neutron?
1 over
1
0.
over
and
0.
1/0n. What's an electron?
0 over -1.
0 -1e. Okay. Out of those 3, which one has no mass?
Neutrons.
All right, she's right. Technically, they all have a mass, but which one looks like it has no mass? Wise guy. Try again. Yes. Mass number's on top. Electron has no mass, but it actually does, and that's what I wanted to review with you. What's the bottom number tell us?
Charge.
Charge, -1, neutral, +1. Okay? Proton, neutron in the nucleus, electron outside. This is actually 1/1840th of a proton. Did I tell you that last week?
Yeah.
Okay? So that is the mass of a proton, or mass of an electron. So you need 41,840 electrons to balance the mass of one of these. That's how small an electron is. So that's why we say an atom is mostly empty space. Because you have a little tiny nucleus with these guys, and then this is on the outside, not really taking up any space. It's so small. So I just wanted to review that. Sometimes I don't think I do that enough. So that's, remember, table O, that's how you look that up. All right. Okay, so we're good with that. I had a bunch of Regents questions we were going to maybe go over. We'll do that tomorrow because that was kind of a long warm-up. All right, take your notes out. Let me review some of this stuff, and then we'll get you out of your seats, and we'll see if we can yank some people around here. All right, so yesterday we wrote down the 4 atoms and ions from the homework. Oh, I didn't really grade these. I probably should have here. Tell you what, Mike here, Morgan Heath, come on up, please. And can you give this to Mike? real quick at the end of class, you three just come up here. I'll spout off the answers real fast. That'll be faster, and that way you'll have it. So we'll do that real quick. So yesterday we went over 4 atoms and ions on that, and then the back we didn't go over. So after I give you some notes, we talk about some things, and play a little tug of war there. If we have time, we'll go through these questions. If not, we'll address these tomorrow. But let's talk about radius here. So atomic radius. And what we learned yesterday about electron configurations and stability of ions, we're going to kind of repeat that again today, and that helps us understand radius. So those of you who didn't look up the definitions, you kind of lost your chance, I guess, except for those of you who weren't here. If you weren't here, then I guess you're getting freebies here. I don't know how else to do this. We got to go over it. So atomic radius, who has a good definition? Who looked it up? Go ahead, Nick.
The size of an element's atoms from the center of the nucleus to the outermost orbital.
Where'd you get that definition? Google. Google, you know, doesn't have all the answers, but I mean, that's an okay definition. She said the size of an atom from I don't know, I'm paraphrasing. I guess I didn't listen
Center
close
of the
enough.
nucleus to the outer part.
From the center of the nucleus to the outermost orbital. The problem is that orbital is doing what? It's moving. Okay, electrons are constantly moving. So it's a cloud. Okay, so electron cloud. So it's kind of morphing a little bit constantly. It's not just a sphere like we visualize. That's good to understand, but it's not exactly how it works. So there is no boundary either. There's no like thing you can measure. So that's not a bad definition. Does anyone have a different definition?
Mine was pretty similar.
Mine was just an atoms. Just the measure of atoms.
Okay, so okay. What if we took 2 atoms? 2 atoms, okay, that were identical, and we put them right next to each other. Okay, I should probably go behind the desk so everybody can see. So, 2 atoms that are identical to each other. Now I'm trying to hold it so you see the very middle of the ball is where the lines kind of connect and make like a cross or a plus sign there. You with me? The black lines there, the grooves, okay, channels, whatever you want to call them. Okay. Okay. How would we measure the radius of one of these by using both of them? How would we measure the radius of one of these by measuring? You're close. She said measure both and divide by 2. What could we measure easily? It'd be impossible to measure the radius because that's like eyeballing it. But what could we actually measure accurately and then divide by 2?
Circumference. You can find the circumference.
Ah, forget that. That's what we did in lab. Good job, but let's do it a different way. Trevor.
You can measure from the black line to the black line.
Right. So that positive, that cross there in the middle, do you guys know what I'm talking about here? I feel like I have a point.
Yeah.
Right here. That point right there, would you argue that's the middle of the ball?
Yeah.
Kind of like the nucleus is the middle, right? If I could put my finger through the ball, it would go right through the middle. Okay, stay with me. This will help you understand the definition. So again, I'm trying to hold it, at least on this side it looks right, pretty close. So if we were to measure from the middle of both basketballs, it doesn't look right?
No, it looks good enough.
Oh, right. Wait, what? How about that? Is that better?
Same thing. Hey, that one.
They're literally the same. What are you talking about?
I don't see no problem.
So you
I
gotta
think you guys
rotate.
just pick.
No, that's good. That's exactly what I want it to look like.
I see it now.
Where do you go?
Twist it. Just twist that ball.
Which way? Like this?
Yeah.
No.
What?
No.
You can't see it on the other side.
This looks exactly the same to me.
No, it doesn't.
Turn it.
Oh! There we go. Whoa! That was messing with my mind. You know, I was so obsessed with the middle, I wasn't even looking at the top or bottom. All right, does that make sense?
Yeah.
All right. Okay. Got it. All right. So you know it's funny. At Thanksgiving, I was at my in-laws, and my wife's brother has 2 kids. They're little. One's 3, one's like 1.5, and they were playing with chalk on the driveway. and everyone's drawing things. So I'm trying to draw a basketball. I drew like 17 of them. I finally had to look it up on my phone. I forgot these lines were curved. They're like, you coach? I'm like, well, I guess I don't look at the ball very often. But anyways, it was embarrassing. Back to this. If we measure the middle of this ball to the middle of this ball, like Trevor said, and then divide it by 2, is that the radius?
Yes.
Yes. Does that make sense to you?
Yes.
So I would wish I had another hand to kind of explain this a little bit better, but from this point to that other point on this ball, if these are 2 identical atoms, make sure I don't screw that up again, that's how it's actually done in real life. You take a diatomic element or a solid element where the particles are really close together, and somehow, some way, they can use maybe an electron microscope, and they measure the distance between the 2 nuclei, and then they just divide it by 2. That's a lot easier because this is not what an atom looks like. It doesn't have an exterior. It doesn't have, it's a cloud, so it's hard to actually quantify. So, but there is a nucleus, so they can measure from this nucleus to that nucleus, divide by 2. That took longer than I thought, but that's how we do it. It's half the distance between 2 adjacent nuclei. What's adjacent mean? Next to it, right. So, hopefully you remember that for a long time, because it was a whole conversation there. That's how they measure the atomic radius. However, now I'm going to digress and go back to what I just said about Google not making sense. If you want to remember from the nucleus to the outermost shell, or outermost orbital, that actually will help you learn as well. So that's not a terrible definition. This is just the real definition. So I'm going to put what Hannah said. So the distance, this is again to help you learn about radius changes. So the distance from the nucleus to outermost shell. Outermost shell. Or from the last shell, or the valence. You know what? Let's put valence shell. Sorry. Valence shell. That's a better way to say it. So this is from the nucleus to the valence shell. That's another way to think of it. Okay. So that's atomic radius. What's ionic radius? Who has a definition for that? Well, you guys all pointed to your stuff when I walked around. Anyone have a definition? Matt Payne.
Radius of an atom's ion.
Okay, it's the radius of an ion. Good, but what does that mean?
Exactly. That's what I had. That's why I didn't say it.
I could have made up that.
Yes, you could have. Ionic radius. It's the same definition as atomic radius, except 2 ions. So if you take 2 atoms, and then either give them electrons or take electrons away, those 2 ions will be right next to each other. And then you measure them the exact same way. So I'm just going to do this. It's the exact same. I don't need to rewrite it. Neither do you. It's the exact same thing, except instead of 2 atoms, you have 2 ions. They're right next to each other. You measure the nucleus between the 2 nuclei and divide by 2. That's it. It's the exact same definition, except ions. So that's why the definition you guys got, that it sounds silly, but that is the definition. So here's the thing we need to know about ionic radius stuff. So I need a little more room. Okay, so I'm going to continue under ionic radius. Metals form cations. What's a cation? Positive, right? Yeah, it's positive. So, go to your periodic table. Look at group 1, look at group 2, look at the transition metals. Go to your periodic table. Look at group 1, look at group 2. Everybody go to group 1, group 2. What charge do you see in the top right corner, Morgan Heath, for group 1? +1, all of them are +1. What about group 2? All of them are +2. Those are cations. Metals form cations. Go to your transition metals. Go to your transition metals. Look at iron. What charges do you see? +2, +3. Go to, I don't know, zinc, Zn. +2. Go to gold, Au. +1, +3, right? Go to silver right above it, +1. Go to chromium, Cr, +2, +3, +6, right? Okay, so those are positive cations. Those are cations. Ariel, what does that mean? How do metals form cations? What do they do with their electrons? They lose them. Good. Metals lose electrons. So, let's use sodium as an example. So, Na is an atom. It turns into Na+1, the ion. Go to table S, please. I'm going to get back to my list here in a second. We're gradually getting there, and then hopefully we'll get to the tug of war. It takes me way longer than I want to do this. But anyways, go to table S. Someone look up the atomic radius of sodium. I'm showing you now that table S is a big help with this.
160.
160 what?
0.0.
I need a unit.
PM.
PM, picometers. That's really small. A picometer, some people call it pico. I like pico. It's like Pikachu. Isn't that what is that? That's what do you call those things? Pokemon, right, sorry. I'm way too old for that stuff. Back to the front of your lab. Go to the very front, table D or C. Where's the ones with the prefixes?
C.
C. What's pico? Or pico?
10 to 12.
Right, look up here. So there's 1 times 10 to the 12th picometers in 1 meter. Okay, so here's a meter. All right, here's a meter. So a picometer is so small, I need that many of them to equal this. So if I was to divide this meter stick that many times, that's how small a picometer is. That's ridiculously small. That's what they use to measure the distance from the nucleus to the valence shell, right? It should be small. Atoms you can't even see, so that should be very small. Okay, so I'm going somewhere with this. Is this bigger or smaller? Here's how you figure this one out. It's easy. The electron configuration is 2-8-1. Write that down. Who can tell me what's the electron configuration of Na+? 2-8. Leave a space here. Leave a space. 2-8. So I don't know the radius of Na+, but I know if it's bigger or smaller than 160. Who thinks they know? Nicole. Smaller. Very good. So I'm going to do this. I'm going to go less than 160 picometers. Okay, I'm going to circle that, make sure you understand. So every time a metal forms a cation, it's losing electrons. Why does it do that? To have a full valence shell. In the process, the radius shrinks. Here's what I want you to do. Underneath here, draw a little atom. So nucleus, 1, 2, 3 shells. You have 2, 8, 1. Now over here, we're going to draw positive with a 2 and an 8. So you can see it shrinks. So every time a positive ion is formed, I don't care what element it is, I just use sodium as an example, the radius shrinks. Why? Because it's losing electrons. And sometimes it's losing a whole shell or layer like an onion, right? If you peel off a layer, it's going to shrink. Does that make sense? Good. So losing electrons, it gets smaller. What about gaining electrons? What do you think? Get bigger. Can I erase this? Okay. Let's use an example for the nonmetals now. So nonmetals form anions. Nonmetals form anions. How do they do that? They gain electrons. So for example, we'll just use fluorine. That's an easy example. So fluorine, which is an atom, forms F-1, which is an ion. 2-7 2-8. This one's not as easy to see. So they both have 2 shells. What's the radius of F, please? Someone look that up. Table S. I want to guess 47. Or 60. Would have been cool if I was right. 60 picometers. Okay, 60 picometers. So, if F gains an electron, it actually gets slightly larger. So I'm going to do greater than 60. Oh wait, did I do that backwards? Yes, I did.
You did it backwards the first time.
I did?
Yeah.
I've never understood these.
Yeah, you did.
Oh, sorry. Flip that then. That's a real bad mistake because I don't want you getting confused. Or just write the word less than or greater than. Okay, so if that's confusing, this is greater than 60. The other one, Na plus, is less than. So I did it backwards. I'm sorry.
Yeah.
So it should have been, what was it again? 1 what?
160.
160, so it should have been like this. That's not what I did? I did that? Sorry. So we're good though? I made that mistake, but we understand the mistake? Okay. So yeah, the Na plus gets smaller, so less than 160. F minus is greater than 60. It gets a little bit bigger. Now, when we draw, I'm not going to have you draw the pictures here because it's confusing. So 2,7 is the exact same size on the board as 2,8. So if I draw those shells, they look to be the same size. This is where this comes in here. Nuclear charge, then we'll talk about these two. And then hopefully, maybe, doubt it, but if we have time, a little bit of tug of war. If not, I promise we'll do it tomorrow. But I got to explain nuclear charge now. So it's really important to understand, first of all, table S is there. You can look up the radius. So any radius question about the periodic table, yes, there's trends. I'm going to teach you that, but you can look it up on table S. Really important to remember that. The other thing to remember is the positive ions get smaller, negative ions get bigger because they're gaining electrons. But here's the concept. Nuclear charge. So this is underneath that fluorine example. Nuclear charge. What the heck is a nuclear charge? It's the charge on the nucleus. And it attracts the electrons. It's the charge on the nucleus, and what does that charge do? It attracts the electrons. Put a star. All nuclei are positive. Why? Protons. Put that in parentheses. Protons. Protons. They're in the nucleus. So every single nucleus is positive. And it attracts those negative electrons. So, maybe I actually can demonstrate this with the rope here real quick. Yeah, I need, how many people do we have? 1, 2, 3, 4, 5, 6, 7, 8, 15. Not enough. We'll just make something up there. All right, so I need 8 of you. Who wants to play tug of war? I'm just going to start calling people out. Obviously not Mike. Courtney, 1, 2, 3. Adam, 4, 5, 6, 7, 8. Go on over there.
Boys?
Oh,
I thought you looked like all girls. I guess there's.
more boys.
All right, give me boys over here, girls down there.
Oh man.
Don't worry, girls. Adam's weak.
Definitely gonna win.
We're not actually gonna play. Can we get the rope out, please? This is just a demonstration.
Pick an end, guys. Pick an end.
Let's not
come on.
Okay, grab the rope. Let's go. All right. Do we have some sort of middle thing? We don't have a middle thing. That's unfortunate. No, that's not it. Okay. Here, hang these around it. Loop that around. We gotta have something to have a vantage point here.
There's 11 knots.
Just put it right there. That's good. Okay. All right. So this is kind of a short rope. We usually use a longer rope. Okay. So now, what camera? No. So we have 4 protons. We have 4 electrons. So for the sake of the demonstration here, if we have 4 protons and 4 electrons, all right. I'm gonna tell you go. When I say go, start pulling. Okay. So, all right. So, you should probably put your hand around the knot. I got it. Okay.
This is right.
All right. So, when I say go, they're gonna pull. So let's make sure we understand this. And it might not. You guys might be stronger than them. We're gonna find out. But so the protons are supposed to be stronger than the electrons. They're supposed to be. Don't cheat.
I'm not.
Yes, you are.
Adam.
So wait. So the protons are gonna pull the electrons in, but you're the electrons and the protons, but it's pretty balanced 4 and 4. So there's a method here to my madness. Ready? Go. All right. Good. All right. Okay. Now set it back up.
Can I get something to my belt?
Okay. All right. Do you want to get involved?
Bro, zoom from over here. They just
Go ahead. Do you want to get involved? Mike. You got Mike's coming over to help.
What is it, 6 on 4? We got this.
That thing, get over there.
Ready? You guys got pull, man.
Okay, now hold it. Let's not lose the chemistry part here. So stay with me. If the protons, the nuclear charge, that's them, have a stronger pull, what happens to the radius? So if the nucleus is pulling the electrons closer, does it get smaller?
Yes.
Yes. Now, what if we start adding a whole bunch of electrons? The radius should get bigger because they're going to start pulling back. Let's find out if the radius gets bigger.
Oh boy, it's
Ready?
upset brewing.
Go! Come on, get him! Pull him! All right, stop.
Holy
All right,
crap.
sit down, please. Sit down. Did you hurt yourself? Sit down. Let's go. Good job, everybody. Now, so
Dude, I have 1 knot on the
here's
back.
the concept with the negative ion. The reason F minus gets larger is because now the protons can't pull as easily. There's too many electrons. I ran out of time. Here's your worksheet. We'll pick that up tomorrow. So, Mike,
Adam goes, okay,
Morgan, and the other Mike, don't go anywhere. All right, do me a favor. Just do this side, the front. The back are radius questions. We really need one more day before we go over those. So do just the front of this, okay? You do need reference tables too. So you guys obviously can go as soon as you get this, but I got to see those people. So sorry I ran out of time there. We'll do more of that tomorrow. Just maybe we'll do that again to see if they can redeem themselves here.